All right, any questions from the last lecture? If there are, as I go through the review, I will please ask. I feel last time perhaps the pace of the lecture was a little bit fast, so I will spend more time reviewing. If you ever feel that way, just send me a message. Okay, send me an email, and I'll try to have an extended review. All right, so today we're gonna talk about lecture 15. We're halfway through the semester. We're gonna be talking about the WKB approximation. I actually don't remember what WKB stands for, and propagator. So hopefully we'll have time to talk about the propagator. There will be an extra lecture. Next lecture is going to be the last lecture that's about quantum dynamics, and I'll talk about Feynman path attributes. I think it's important for your general understanding of quantum mechanics, even if you're not using path intervals. It gives you a very different perspective. All right. So, what did we do last time? Let's see. So last time we started by talking about the following way of splitting the wave function. We said the wave function written in a position space, right? So this was what we focused on. We're talking about wave function of particles that move around in space, right? This is a complex function of space and time. So it's natural to take out its norm, the absolute value of it, right? The square root of rho. This is a real function and actually a positive function, rho of x and t, right? Why is it positive? Because it's just a probability density is psi squared, right? Remember Max Born's whatever probabilistic interpretation of the wave function. And then there's a phase that we wrote as e to the power of I over h bar, a function, right? That we said has to be real, right? Why is it real? Because it's a phase, right? And the goal of this splitting was to actually give you some more intuition on how, what the position, what the wave function position variables signifies. So this rho is of course a probability density, right? It's just nothing but the wave function squared. But because it's a probability density. So if the probability of the particle to be at some epsilon tiny ball around a point x naught in space would be the value of this rho function, which is the norm of the wave function, multiplied by that infinitesimal volume at that point, right? Is that clear? This part is rather straightforward. Then we said, well, every time we talk probabilities, you better want to preserve them. So there's a conservation of probabilities, right? Does anyone know? Okay. All right. The conservation of probability tells you that if you have a region of space, right, the amount of, so as the wave function evolves as a function of time, right, the net change in the probability for the particle to be in that region has to be equal to a probability flux that comes in, right? It's just this you've seen in classical physics and fluid dynamics, like not even fluid dynamics, the very basics of fluid dynamics. Continuity equation, you've seen it in electromagnetism, right? Hopefully you recall electromagnetic continuity. Every time you have a conservation law with a local current, right? What does that mean? Every time you have a conservation law, a conserved charge that could be written as an integral over space of something, a current, right? Then you have a conservation law of this nature, right? For those of you guys who are more like, cool. Anyway. So this is called the probability flux, and in this case, we could just cook it up by the virtue of the fact that this psi squared has to satisfy a pole, has to satisfy a continuity equation. How do I calculate J? I just plug in, I just take rho to be psi squared, norm of psi and take a derivative and set equal to 0, right? That's how it's calculated. And then you repackage. From that, you find the result, whatever the right-hand side is, you write it as a divergence of some vector, and this is here this, right? So this is what the vector is. Now, importantly, when we did this assignment of variables, like separating the absolute value and the phase of the wave function and plug it in, you find that the probability flux is nothing but rho over m and the spatial gradient or variation of the phase, right? So you might be tempted to just conclude quickly from the fact from Born's rule that the only thing that controls the probabilities are just rho, right? The absolute value of it. But the continuity equation immediately tells you that probabilities are conserved and there would be there has to exist a notion of a probability flux, which is controlled besides rho, it's also controlled by the spatial gradient of the phase. Good? Short pause here. Are there any questions about this? Conceptually or not? Yes. Which P? No. Where are you? Which line? Here. So j of x and t is minus I h bar over 2m psi star nabla psi minus u this, okay? 2 rows down here, square root rho. Yeah, there are no p's here. Well, all I did was I took psi, expanded this way, square root of rho phase, and I plugged it in here. That's all I did. Previously, it was in 2 separate slides. That's what might be wise. Is that good? All right. So to get some intuition about this, it's helpful to think about just a plane wave propagating in space, right? A plane wave propagating in space, the wave function of it is this, right? And by the way, does the plane wave, what is the plane wave? Is this the solution to any Schrodinger equation? What does a plane wave signify physically as a wave function in quantum mechanics? Free particle, exactly, right? Because we saw that the Hamiltonian free particle is p squared over 2m, right? So the energy eigenkets are just going to be momentum vector, momentum eigenvectors p written in x coordinates. This is what psi of p of x prime is, right? And this was, you remember, 1 over square root 2 pi h exponential, this phase, right? So this is basically up to a tan e2 minus plus pi p x over h bar, right? And then, well, this is an energy eigenket. Under time, it evolves by phase. What is that phase? It's e to minus I e t over h bar, right? And then in this case, e is simply p squared over 2, right? So that's the basis of this example. So it is a wave function. So in this simple example, you see that the nabla of S, the gradient, it's been so long since I called these like I work with this notation. Forget what it was like. I call it nabla, slash nabla in LaTeX. But this is called gradient, right? Yeah, gradient. Which one? Here's P, yes. Here's P, yes. Yes. So here's P next to rho. I'm sure there's a machine learning algorithm that could look at this, cat dog P rho. I don't know how successful it would be on my handwriting. But anyway, all right. So here, what you do is you take psi, right? What is the rho in for this side, it's just a constant, right? I have not written it down because it has no x or t dependence. So this whole thing is a phase. This whole thing is the up to I over h bar is s. So s here is px minus et. So when I take the gradient of s, I just get p as the momentum, right? So that means that plugging in here, your probability flux is just rho times p over m. In classical physics, p over m has a name, is velocity, right? So plugging that back in, this really matches your continuity equation from fluid dynamics equation, right? Del rho del t. Rho is the density of the fluid at a point, right? As a divergence, we call divergence, of rho velocity, right? Because it's a flux. Flux is supposed to be rho times velocity, density times velocity. Good? All right. Then we talked about the classical limit. This is the part that I said was a little bit rushed, so I'll try to spend more time on this, but it naturally blends in with what follows. All right, so what was the deal? We talked about, in this course, we talked a lot about we defined what dynamics is in quantum mechanics, and what came out was the Schrodinger equation, or the Heisenberg equation, if you were talking about operators. I started this part of the course by drawing an analogy with classical mechanics, right? And how using phase space language and Hamiltonian dynamics to make it look more natural. But we saw that in going from classical mechanics to quantum mechanics, there was a variable, there was a dimension-full parameter that was introduced, h bar. If you recall, we had to introduce it. And the dimensionality of it was fixed, right? Actually, as a matter of fact, you could have argued this here. Yeah, when you write psi this way, a phase is always dimensionless, right? That's sensible. You can only exponentiate a number. You cannot exponentiate a kilogram. That makes no sense, right? So it has to be dimensionless. So what we are doing here is that we know that this dimensionless number behaves like action. So it has to be action over something, a constant that has the dimensionality of action, and that's h bar, right? So now the question is, how, if we take h bar away, is there a limit of h bar going to 0 that gives you back classical physics, right, that you're familiar with? Is there a systematic expansion in h bar? Or it can't be a systematic expansion in h bar because h bar is dimension full. So what is that expansion? How do you get classical physics back as a limit? So let's start with the Schrodinger time-dependent. Okay, I don't like the way that Sakurai calls this wave equation. Let's call it the Schrodinger wave equation, because the wave equation is something else in physics. All right, consider the time-dependent Schrodinger wave equation. Here it is, right? And plug in this rewriting of the variable, separating the phase from the absolute value. And then what you would like to do is you would like to organize every single term in terms of powers of h bar. We did that last time. There were terms that were h bar independent. There were terms that had h bar and then h bar squared, but that's on high orders, right? So the idea was to drop all the terms that had explicitly h bar in them. But to argue for that, we saw that you can't say h bar is small. What is small is h bar times, this is the the Laplacian of s compared to the absolute the gradient of s squared. So this is the approximation we had to use, and today my goal is to give some insights as what this approximation is doing physically, right? You already saw that nabla of s controls the flux, but this you don't have an intuition about probably at this point. So the goal is to give you some intuition about this. Actually, that's not what we're going to do. What we're going to do is that we're going to divide the right-hand side by this and try to give you an intuition of the right. That's what we're going to do. All right. So after you did this approximation, what you found was that Schrodinger equation gave you this equation. Del T of S is this thing, which by reorganizing the terms, bringing this guy to the left-hand side and there's this guy here, you recognize this as the Hamilton-Jacobi equation for classical mechanics. So we did recover classical mechanics in this limit. So what remains to be done is to justify what the hell is this approximation. Good? Yeah. Oh, beautiful. No. So this is a beautiful, beautiful fact. Let me think how to say this. The question you could ask is this: how did we discover quantum mechanics? We had a classical system. There were electrons that were going out, spinning a hydrogen atom. This is a classical system. It was behaving weirdly. So what we did was we recognized that we have to correct our classical equations with these H bar stuff to make them correct. And then there was wave function, all of that. But there are examples of systems that are purely quantum mechanical and have no classical analogs. There are such examples. What is an example? We already discussed one of those. Spin, right? When you discuss spin, there is no limit of H bar going to 0 that will give you a vector spinning, and there's simply no limit of that. This is how quantum mechanics stretched our mind in physics. There are quantum systems that simply do not come from quantization of a classical system. This should be very important because it really changes the rules of physics. Right? It's not like the classical world is the basis of everything. There's some H bar floating around. Spin, there's no way of classically describing it in any limit whatsoever. As a matter of fact, so spin, let me just go on a quick tangent. In quantum mechanics, the fact that electrons have spin is just something that you have to assume. It turns out later on that it needs to be there because of relativity, blah, blah, blah. All right. Any other questions? That's a conceptually important one. Yeah.
So how does it relate to the limit of large quantum numbers?
Yeah. So that's still when you talk about there's a classical system called an electron orbiting hydrogen atom. Right? There is a radial potential. You solve that, there's something. And you get a mismatch between that and the quantum answer because there's an H bar playing a role, right? There are two ways to recover your classical physics. First, you take the H bar going to 0. But it's not like I have a dial in the world to turn H bar down. That's unphysical. Another thing you could do is you could try to look at certain solutions of quantum mechanics that behave almost classically. In this case, it would be high angular momentum stuff. But yeah, so that's basically that's different from classical limit. Those are quantum states that behave similar to classical states. Like another example of that was coherent states, right? Coherent states has some flavor of classical behavior. All right, any other questions? Good. So, all right, this is important. If there are this is a natural moment to pause because going forward until the end of the lecture, I'll make one extra assumption and I'll focus on that. So everything is what we're going to work in with whatever we did, which is this splitting of degrees of freedom. What is that extra assumption? I will stop talking about a general quantum state. I will talk about stationary states, otherwise known as energy eigenstates. So whatever follows from now until the end of this lecture, until we start switching, talking about propagators, we get there, it will be about energy eigenstates, right? Stationary states, that's another name we gave it. Why did we call energy eigenstates stationary? Expectation value of any observable, otherwise known as the self-adjoint Hermitian operator, is time independent energy eigenstates. All right, good. So what is the deal with energy eigenstates? The deal with energy eigenstates is the following. Remember the splitting we were doing? What we were doing was that we're writing the psi of x and t as square root of rho of x and t e to the power of I s over h bar, right? We are splitting the phase and the norm, absolute value, right? Normal people call it absolute value. All right. Now, when you take a stationary state, the time dependence of the stationary state is simply like that. It's just an exponent, e to minus I e t over h bar, right? So the wave function, the x dependence of the wave function could contribute to a phase, but the time dependence of it must be of this nature. Time cannot contribute to the absolute value of the wave function. That's the lesson. These states are special in that. The absolute value, it's just a statement that rho probability density has no time dependence. d dt of rho is 0. And let's establish that. It must be, right? Because here is space. If so, rho at this point tells you about the probability of having a particle there. If d dt of rho was non-zero, I could take an observable that's exactly localized here, and that observable, its expectation value had to be time dependent, right? All right. That means that for an energy eigenkette that Sakurai uses this notation for, it must be that you could split this action into two parts. W of x, a function of x, minus et, right? The time dependent, there is no time dependence in the absolute value part, and the time dependence in the phase must be just minus et. Whatever is the remainder, we're going to call W of x, right? This is a trick used by Hamilton in understanding classical physics. This is called Hamilton's characteristic function. So you might immediately complain, what are we talking about? We're talking about phase of the wave function. How did Hamilton talk about wave function? He didn't know about wave function. Hamilton didn't care. He talked about waves, right? He didn't have h bar in his game, but this equation has no h bar in it either, right? It just said that the phase of in classical physics, we have stationary states. So he was talking about phases and stationary states and things like that. All right, good. So is this point clear? This is usually something you learn in classical mechanics, and I understand that have you guys seen this before? You have. Oh wow, that's pretty impressive. Because usually this is like an advanced classical mechanics. Somehow we've cut this stuff out of classical undergraduate education, classical mechanics. All right. Why do we do this? The reason is we're gonna use this stuff to design an approximation method for solving Schrodinger equation that's time independent. So a time independent Schrodinger equation is a Schrodinger equation that holds for energy eigenkettes. That's our goal. Let's nail that. So we want to talk about energy eigenkettes, hence the time independent Schrodinger equation. We're going to focus on that, and we're going to use the knowledge, the fact that the phase of these guys should have this form to design an approximation method for energy eigenkettes. Is that clear? This approximation method is called WKB. It's extremely powerful. If you ever do AMO physics, it's all over the place. It's extremely powerful. I cannot stress this enough. It's also a route to a whole bunch of other stuff in physics. I might have mentioned this before. Quantum chaos. All right, WKB approximation. It's going to be in nature an approximation that, well, it's called an approximation because it's not, because you're neglecting a bunch of terms, right? You're dropping a bunch of terms and considering them to be small. These terms are going to be terms that are exactly small in the sense that we discussed. There was this small approximation that I said. Right, let me write on the board so that you guys can remember it. It was this. So it was h bar had to be much smaller By the way, in physics, this kind of approximation occurs all the time. Something is smaller than the derivative of a function square over the second derivative. You already have an intuition of what it means. The second derivative is about curvature, right? This is the rate of variations. Just think about that a little bit. Yeah.
So someone who's like slowly
Yeah. Any function that's like this is almost flat at that point. So we'll see. We'll see this. It's slowly varying. A function with this property, right, is slowly varying. Well, sorry, I think I might be dropping terms here. Am I dropping anything? Let me see. Where was my approximation? No, I'm not dropping anything. Okay, good. Good to know. All right. So to repeat, we're gonna restrict ourselves to one dimensions for simplicity. None of what I say is specific to one dimensions, but just for the sake of to be explicit and make it simple, we're gonna talk about wave particles moving in one dimension, space dimension, and we're gonna approximate the stationary states, energy eigenkets. We said that for energy eigenkets, we could split the action into W of x, Hamilton's characteristic functions, minus ET, right? We also saw that the gradient of S, right, had naturally the interpretation of classical momentum. Remember that bit? For a wave, we saw that, right? Why do I say this? This comes from the continuity equation, right? So we wrote the continuity equation as del T of rho plus divergence of rho. Well, we wrote the P over M. This guy was delta of S plus. Right? This was my J. I had a slide that said J was rho over M, nabla of S, right? And if J is to be interpreted as rho times velocity, whatever the hell that means, then it's natural to interpret nabla of S as classical momentum. That's hence this, right? So what I'm trying to do is I'm trying to motivate an approximation, an ansatz for the wave function. Is that clear? Does everyone know what an ansatz is? If you want to solve a differential equation, an ansatz is, let's say you're trying to find a function psi of x. An ansatz is a guess of the form of the answer. So you say that this, I'm gonna assume that it looks like, I don't know, something e to the power of I, some particular functionality. You plug it inside the differential equation. If you could solve the equation, it's a solution. So an ansatz is an educated guess. That's what it is. It's a German word, I believe. Right? That's what it is. What we're trying to do is, I could just present the WKB approximation as a very brilliant guess that works. But what I'm trying to do is that I'm trying to tell you guys how this guess was derived, because it's intuitive. Good? All right. So the idea is the following. For stationary states, delta S, can't talk. Gradient of S had the interpretation of classical momentum. And because S for stationary state is W minus ET, this would be just the gradient of W. Right? Everyone's with me so far? All right. Then for classical states, we also expect that P classical squared over 2m plus V of x is the energy. So from this equation, I can write the second equation for P, which is square root of 2m E minus V. Putting the left-hand side equal to right-hand side, you find the following. You find that this should be square root of 2m E minus V plus minus. Equal to P classical. Right? Is it clear what I did here? So this is the first line here. This is rearrangement of the second line. Then now I can integrate this guy in one dimension. It's straightforward to integrate it. And this is what it looks like. So what did I do? Plugging this back into S, I found a guess. Notice that a lot of this is heuristics, right? In quantum mechanics, there is no such a thing literally as P classical. This equation does not literally hold because you have to solve for operators. It's an operator equation, right? But this is heuristics to come up with a form, an ansatz, right? A guess for the action, which is going to be the phase of the wave function. So this is our guess for the phase of the wave function. Good. There are a bunch of things that are happening that are really funky. I'm hiding a bunch of things under one thing, very important thing, under the carpet. I'll hint at it, but something dramatic happens at some point, which, well, it won't look dramatic on the slides, but conceptually. All right, so is everything okay with this? How I motivated this phase for the wave function? For the wave function of stationary states, yes. That's all catch. So this equation is only sensible when P is larger than V, right? Why? Which step of the way did I use this? If V is larger than E, which step of the way falls apart? The second line, P classical. So when E is larger than V, this is a classically allowed region. When V is large, when E is larger than E. When V is larger than E, it's a forbidden region, right? And you will actually see we're gonna push this to the regime where it's forbidden by classical mechanics, right? And then you already talked about, right? You've already talked about this. If you have some sort of a potential like this, right? Classical particles, to be able to propagate in this environment, will have to have energy above the potential, and then it just like propagates and goes through. And this is the physics we're discussing here. Good. Quantum mechanically, if the particle doesn't have energy, enough energy, if this energy is below their potential, right, it can't exist. We're not talking about below the potential out at infinity. This equation is solved at every point in space. At every point in space, we're going to switch to the forbidden region. So that's the catch, but you don't know that for now, okay? Any other questions? All right. Very good. So here's a few lines of algebra. I might have to go through them fast, but they're very straightforward. Okay, so I absolutely recommend that going back to this and looking at it. There's nothing here. There's no magic. It's just a few lines of algebra. So what is the deal? For stationary state, an energy eigenket takes this form, right? And I plugged in already the form we know from for the phase. Rho is time independent. We argued for that. So del T of rho has to be 0 for all x, and every point in space, the probability density should be time independent. That means that if you write down the continuity equation, which in one dimension is like this, right? I have it on the board already, right? So all I'm doing is, in one dimension, this is del x. I'm plugging in this is del x. This is my equation, yes, and I've taken them out, right? Continue the equation, right? Now, for energy eigenkets, we know that this term is 0. So this term must be 0. That's it. Right? Conservation tells you that this term has to independently be 0. From which you learn that rho del x of S over M is a constant. From which you conclude that rho has to be, what do you conclude? Has to be 1 over del S of x times a constant. Right? That's the only way for it to be. Good. But then remember that we know what del S of x is. This was our form, suggested form for S. Take a derivative with respect to x, you get square root 2m e minus v. So here it is. We learned that square root of rho has to be constant over e minus v of x to the power of a quarter. Just one line of algebra. There's really nothing fancy there. And remember that e minus v is roughly speaking momentum squared, classical momentum squared up to 2m. So this is roughly speaking like 1 over square root of velocity, classical velocity, if it existed. But it doesn't. Good? Let me pause here and ask for questions. Because maybe this a few lines of algebra was fast, but there's rather straightforward. I tried to reproduce it, right? All I did was that I knew that S, I had an ansatz for S, took a derivative with respect to x, and that gave me square root of e minus v up to a bunch of constants. That's my equation. From that, I learned that if I take a square root, I'm going to get this equation. That's my equation. Good? Quarter.
4.
Quarter. 1 over 4, yes. Yeah. All right. Very good. So what did we learn? We learned that, oh, our ansatz not only fixes the phase, but also gives us a suggestion for the time, for the dependence of the absolute value of it, rho part. So here is the full answer. Here is our full ansatz, right? This is now a consistent ansatz called the WKB approximation to stationary wave function. So let me just go on a short rant here. What did we do? We took energy eigenkets, and in analogy with classical physics, we wrote a guess for the phase part. But the point is, we had said this before, you can't just independently come up with a guess for the phase part and ignore the consequences for the absolute value, because they talk to each other. The continuity equation tells you that the absolute value of the function, the absolute value of the time dependence of the absolute value of the wave function is related to the phase. So for your approximation to be consistent, or sorry, for your ansatz, for your guess to be consistent, you have to also take into account the implications of the form you suggested for the phase for the absolute value. And here it is. That's what we did. That's literally what we did. And this is our complete guess for the wave function. Let's stare at this and see if you have any questions. Yes. Say it again.
Don't we need to know E?
Absolutely. What are we trying to solve for? An energy eigenkett. Which energy eigenkett?
Yeah, I guess it's,
The wave function on the left is labeled by an E. Okay, that's a beautiful question. I plug this into the Schrodinger equation, and what do I find? If I can find a solution for any E, well, that means that there's an energy eigenkett for any E. That means that there's a continuous spectrum, right? For the Hamiltonian operator. If I plug it in and I find solutions only for particular values of E, that means that there's some quantization happening, right? That was a very good question. Okay.
So essentially you need to take that, plug it in, and then.
That's the idea. So all I'm doing, I could have started this lecture by saying that, oh, you could do this. Here's a guess for the wave function. Use it whenever you're trying to solve for Schrodinger equation for energy eigenvalues. That would be the end of the lecture. But this approximation comes from somewhere, right? And that's what I'm trying to argue for. Yes.
I don't understand what the guess is. So it seems like we just arrived at this.
We did not. These are what I did was I wrote this equation. So 1 plus 2. This is an eigenvalue in some eigenvalue, like eigenvalue problem. There is no such a thing, such an equation. This is just classical analogy. There is no such an equation ever in quantum mechanics. These are the things that I have to find by solving a differential equation, right? The other thing that I had was this delta of S interpreting as P classical. That was also heuristics. That's true for classical waves. And then I said this is equal to that. This P is the same as this P. That was the origin, right? Yes. Then miss a 2m in the first slide. No, I wrote the constant.
So it was something about
Be classical by what? So when I put that wiggly thing, this means proportional to. It means that there could be all sorts of factors of constants, like mass, dimensional constants in there. B classical, what it means here is what I meant by B classical is P classical over M. That's all I meant. I wrote it that way because there's like in Sakurai, there are 2 paragraphs about that. I read the paragraph, it's not like enlightening, but I thought maybe I should write it this way in case you read those paragraphs, and it has a different effect on you. All right, are we good? Let me see, how am I doing on time? I'm doing pretty well, actually. All right. Everybody's with me? So in summary, this is a guess motivated by some classical heuristics that we're going to plug in to solve and find energy eigenkets. We're going to try to plug this in to a Schrodinger equation for time-independent Hamiltonians, right? There are things that are funny about this. Yes. So I absolutely recommend that just staring at this. There's so much you can see in this. The only solutions you have solved for so far, the only Schrodinger equations you've solved for so far is just a free particle, right? The solution to which was a plane wave, right? The plane wave had a phase, right? Which was what sat up there was P over M minus ET. So just take the exponential is 1 I over H bar, put the rest in parentheses. That's Px minus ET. Minus P squared over 2m T, because E is P squared over 2, right? That's because V is 0 and E is P squared over 2m, right? So that's what the sort of that is. And there's no x dependent, the integral gives you an x. The other solution that you know is the only other thing we solve for. Harmonic oscillator, right? In the case of harmonic oscillator, what is your V of x? As half mx squared, right? And E minus that, you could plug it in and see what you get. But here's an interesting thing. We made a funny, interesting observation. The solutions to our energy eigenkets for the harmonic oscillator, they all came out to be real. Recall? They all came out to be real. So that phase, something should happen. Just there's so much you could just stare at this, but this is an approximation. This is heuristics, right? Good. Well, actually, there's more to what I said, because All right, so now we're at a place where we could talk about this weird approximation we made to get the Hamilton-Jacobi equation. I think I erased it on the board with the intent. I wrote it on the board with the intention of not erasing it, but I managed to erase it. All right, so what are we gonna do? I'm gonna only argue for the physics of this approximation in the case of energy eigenkets, right? That's all I'm gonna do. For energy eigenkets, we had a form for S, which was W of, sorry, that's a typo, W of X minus ET. This is the Hamilton's characteristic function. So these are spatial derivatives. ET drops out. This is my approximation for energy eigenkets. Good. But then the WKB also gave me a suggestion for what W is. Here is W. What I'm gonna do is I'm gonna plug it in and take derivatives, right? So in short, let me just write on the board. All I'm doing is that our classical approximation came out of this. I'm looking at the right-hand side for energy eigenkets, right? In the form that we found for the phase of an energy eigenket in the WKB approximation. That's all I'm doing. So I'm working out the right-hand side to see if it becomes something more tangible. It will become something more tangible because what's on the right-hand side is going to be only dependent on W, and W is just a function of E and V. So at the end of the day, it will become a statement about H bar compared to V, EZ, or EMV, right? So that's where the intuition comes from. For generic state, S is not intuitive. For energy eigenkets, we relate it to things that are intuitive. Good? All right, so let's do that. Here's the equation you find. You rearrange stuff. You divide, you bring this down here. M cancels out. You get this equation. Let me just first focus on this equation, right? This is really nothing fancy. It's just a rewriting of what we had. This is just this equation. But now I'm going to try to interpret this. This says that H bar over this value that we already argued to be intuitively classical momentum is much smaller than E minus V of X over dV dx. The left-hand side in early days of quantum mechanics had a name. It was the I don't know how to pronounce the Broglie. It's a French name. Broglie wavelength. It's a wavelength associated with particles based on their momentum. And this says that the approximation would be correct when the Broglie wavelength is much smaller than the right-hand side. So let's work out the right-hand side. The right-hand side says how much E minus V changes over the derivative. I encourage you to stare at this equation and extract the lesson, the intuitive picture that I'm describing. Here's your V of X. This approximation is basically saying, so the Broglie wavelength controls how fast this wave function is jittering in space. Is that clear why? Let me clarify this. So what I'm doing, I think I absolutely have to clarify this. So my energy eigenket in the WKB approximation was something e to the power of I over h bar, right? Integral 0 to x or whatever d of x prime square root of e minus d. Sorry. Minus I, right? The picture I'm drawing here is the wave function at a particular time, t equals 0. Take that away, right? Good. So I'm staring at this equation. There's 2m in here as well somewhere. This is about this object, right? Which is the inverse. Oh, actually, that's just 2m. Sorry. This is the inverse of what I had here, right? If this is large, the left-hand side of my equation is small, which is my approximation. So this means that the wave function, this is the phase of the wave function. In my approximation, the phase is just oscillating insanely fast in space, right? It's just very, very oscillating really fast. Fast compared to what? This quantity. And you could convince yourself this quantity is basically talking about the range of changes, the scale at which the potential changes, right? So it basically means that you're working an approximation where the potential in space changes very smoothly, very slowly compared to the oscillations in the phase of the wave function. That's approximation. So here's the potential. Here's my potential, right? This is space and this is the x. I'm also going to plot the phase as a function of x. This w of x. It's going to oscillate, right? At any point. Pick it at any point, right? It's going to oscillate something like this. It's there. If I zoom in here, if I zoom in a lot, I'm not going to be able to see the oscillatory behavior of the potential. It's going to look basically flat. But this oscillates so fast that even after zooming in, this is still oscillating. That's the approximation. The oscillations of this is way at smaller scale than the potential. From the point of view of the oscillation of the wave, the potential looks flat at every point. Right? Yeah.
Generic state doesn't have.
Of course it doesn't. This is why it's an approximation. It's a lot of heuristics here, right? But you, of course, you will not be surprised if I told you that the wave, we know the Schrodinger equation, but solving is actually exactly is almost, we never do that ever. Like very rare, right? So these approximations play a key role in most of what we do as physicists. That's why we're going over them in detail. Now, most approximations, so this is the sort of these are the low-hanging fruits that were invented in the early days, based on the intuition of classical physics. This approximation is particularly nice because it's based on the intuition. But you should also know that this there is no nice approximation like this for systems with no classical. This is just for motion of a bunch of particles in some potential, whereas there is a classical limit. All right, is this point clear? So you probably have to stare at this a little bit more detail. But another way of, I also encourage you to think about it this way. This in physics, I erased it. This in physics comes up a lot. If you have a function, v of x, right? I don't know if you guys see it, maybe I can write it here. If you have a function v of x, and you have another function, y of x. Sometimes we work in this approximation. I want to say it that way. No, sorry. We have v of x, and we talked about del x squared over del x squared v of x. This is defined at any point. If this is much larger than 1, right? If this function is dimensionless, the dimensionality is correct, right? This has 2 powers of 1 over x, and this has 2 powers of 1 over x. That's why we're dividing. This means that this dimensionless function is varying slowly. Right? I can't say, if I want to say a function that has dimensionless as a function of x is varying slowly here, can't say that because X is dimension 4. You say, oh, but in which units of X? I'm going to change the units of X, and all of a sudden it's going to look it's varying significantly. So the only meaning to something varying slowly has to come from some dimensionless quantity, because del X of V is dimension 4. You can never say del X of function is small. There's no such a meaning. The only meaning that you could build out of it is this. This is calculus. So it might sound magical, it might sound weird, but it goes back to principles of calculus, right? Is that clear? Just a random comment. There's something called inflation theory. That is the most successful theory of constructing cosmology. It describes so much in the world. There's an approximation called flat potential for this hypothetical particle called inflaton. This is what that approximation is. It's essential to get inflaton. It appears all over the place in fundamental physics and in just like ordinary day-to-day laboratory physics as well. So this is called flat potential. This is actually the name for this is flat potential. Flat, right? It makes sense. It means they slowly vary. Any questions about this? Okay, now we get to the point that I have to tell you about how I was hiding things under the carpet. The conversation came up earlier, so it makes my job easier. And the ansatz we had for the WKB approximation here, I had I over h bar integral over this. This is sensible if E is larger than V. That's a classically allowed region. What if E is smaller than V? My classical analogy falls apart, but as an equation, I can say I get square root of -1. That's an I. It comes out, and it will basically gets rid of this I. So I can. This is all guesswork anyway. This allows me to write the guess for the ansatz for the wave function for energy eigenkets in the classically forbidden region, deep in the quantum region. That's where it's interesting, actually. So here it is. When E is less than V of X, I've switched I've taken minus sign out of it. That gives me an I, and that gets rid of this I. Here's a guess. Now we do remember that even our heuristics falls apart here, right? This is classically forbidden. So what do you expect? We talked about this before. When your potential energy, when your energy of the particle is higher than the potential, you expect classically and quantum mechanically for every energy to be allowed, right? We expect the spectrum of the Hamiltonian to be continuous. If your particle has enough energy to just float around, make it to infinity wherever it wants to be, there is no quantization. Right? Is that clear? We talked about this. If the energy is less than the potential, at least at some points, then there's room for quantization. We're going to see how this equation leads to quantization, some intrinsic discreteness. This stuff is profound, honestly, and I think, I don't know, maybe some people understand it deeper, but there is a lot of interesting stuff about this extra I that just we talked about. All right, so what I'm going to do is the following. I'm going to tell you how a sample calculation, you could do calculations. There are calculations of this type in your Sakurai, in the homework, I'll give you a calculation, but let me explain how we'll use the WKB approximation. Imagine you have a potential like, I don't know, like this. It goes all the way to it. It does something funky here, right? Actually, yeah. Good. This is my potential. Let's say my goal is to find or search for an energy eigenket of energy E. I'm going to draw the energy E somewhere in this plot. This is E. At this 2 points. I'm going to call them x1 and x2. Something significant happens. Above it is classically forbidden. Below it, that's right. No, above it is classically forbidden. Below it, yeah, that's right. Below it is allowed. Right? So what am I going to do? For this splits my Schrodinger equation. I have to solve the Schrodinger equation that's time independent. That's the differential equation in X, right? I'm going to solve 3 different differential equations. In this region, region 1, in this region, region 2, in this region, region 3. And then I'm going to put boundary conditions so that the solution on the region 1 matches the solution in region 2, matches the solution in region 3. This is a method we use a lot in differential equations. But because I know here is classically forbidden, I'm going to use this ansatz. Here is classically forbidden, I'm going to use this ansatz. In the middle, I'm going to use the ansatz that had the I over there. Or I can just say I'm going to use WKB approximation. Every time I get a minus, I get a minus sign under square root. I treat it as I, bring it out. Right? That's what this is. Everybody's with me? Yeah, so I have it on a slide. Yeah, so let's say this is my potential. And let's say my energy of the particle is 0. So I have scaled my plot so that the energy of the particle is here, 0. In this region of space, this is space. If I look at, in this region of space, V of x minus E is positive. Right, in region 1, to the left of x1. In this region is negative, in this region is positive again. So what was your question again? Can you ask?
I was just wondering if, like, it's based on that, I didn't know if the quadrant 2 is below the x.
Oh, yeah,
below
quadrant 2 is.
Yeah.
It's just a range in x. Okay. All right. There's one more thing to be careful with. You do know something crazy is happening. What was our approximation? Our approximation was slowly varying functions, right? That meant that the slowly varying potential. That means that the phase had to oscillate really, really rapidly, right? But what is the phase? The phase is controlled. Oh, sorry. Oh, I have it on the slide. So the phase schematically looks like this: e to the power of I over h bar square root 2m e minus v, right? That's the phase. So what happens at points x1 or x2? You get 0. At this point, no matter how fast or how slow v is changing, there's no way you could satisfy your approximation. So basically, in this region that I'm drawing, in the vicinity of x1 and x2, my approximation breaks down. Deeper in the middle or farther out from these points, my approximation is valid. So here's another point of view about the approximation. You got to be careful. You can't take your solution literally near x1 or x2, because your approximation falls apart. You could see that explicitly. Because the phase is?
That no longer stays the phase, right? If you go outside.
Yes.
So then your phase is just deviating.
Oh yeah, but so okay. So I motivate if you take this form and ask what is the approximation that led to this form, I just motivate this point by taking a minus sign out. You are making that approximation. It's no longer the set of words you put to it is not phase, but it's still the same thing. Potential varying slowly compared to what you would have called phase. This guy. Yeah, good question. So it falls apart near here. So the way to solve it is, as I said, you solve the equations here, and in the middle. Now, something really funny happens. Let me, it's on slides and I'm running out of time. I'm just gonna explain in words this way, and please do read Sakurai's discussion of this because it's an explicit calculation. I have like 5 minutes. I can't go through an explicit calculation. But let me tell you in words what happens. So let's consider the following setup where this potential is symmetric. X1 and X2 are just like X1 is minus X2. Right? Consider that. Then my Schrodinger equation would be symmetric. Whatever I solve here, I have to be able to solve here. Whatever boundary condition I have for matching the whatever the value of psi of x at this point is, it will have to be the same value on the other side. So what do I find? In between x1 and x2, I'm solving a Schrodinger equation with Dirichlet boundary conditions at finite distance apart. I have a wave function that has to reach a point here. At some farther distance, it has to reach the same point. This means that you have quantization. Why? Because of this. So in the middle, so here's your x1, here's x2. And now I'm plotting psi, the phase of psi, phase of psi, s of x, right? I'm plotting s of x. Or E of W of x, right? Remember in this part, this is classically allowed, so it's a phase. It's an actual genuine, honest to goodness phase. So here my phase, let's say, starts at 5. Whatever it is, starts here, it has to be the opposite over there, because it's a specific. So it's a phase, it's gonna oscillate, right? Gonna oscillate, and then it has to come back. Because it has to come back, in between x1 and x2, it has to go through a finite number of oscillations. That gives you quantization. That tells you that integral x1 to x2, what would have been p classical, has to be n, an integer, right? Multiplied by h bar up to a phase. Our phase is here, right? Where's the h bar coming from? Because the phase, this w of what I have is the phase of I h bar. So this comes back where it was if it becomes, say, 2 pi n h bar. So I'm also sloppy with pi's and all that. It's actually the pi is taking care of this way. H is 2 pi h bar, right? You recover, actually, so if you, the example that Sakurai goes through, there's actually a shift here that's important. And I sort of qualitatively argued based on symmetry, the symmetry is not required at all. It has to start with the phase here, it has to end up with a phase on the other side. You can't continuously, you cannot continuously vary E and satisfy the boundary conditions, always. So you always end up with quantization principle. That's visible even in this heuristic setup. This is a very, very deep statement. It's a route to a quantum. Hey, also, you have understood so much about this. It's an important observation. But even in early days of quantum mechanics, this play a crucial role, right? There are no quantizations in the classically forbidden, out here, or out there. So Sakurai goes through in more details. Here's the condition you find. Integral from x1 to x2, d of x in one dimension of square root 2m e minus v has to be n plus half pi h bar. So this half must be there. I didn't have time to argue for it. You have to actually solve the equations to see where the half comes from. This tells you the following principle. Let me just say it in words because I'm running out of time and I didn't get to the propagator. But it says the following. Sorry, I think I missed something. I messed this up. So what you obtain is essential that is n plus half. So what you say is that if you integrate from x1 to x2 and integrate it back, you pick up 2 halves, right? And that's a quantization. So I did not argue for that. I should have done the exact calculation. I'll try to include it next time, right? But this half is important. You go and come back and you pick up 2 halves. The quantization condition is written this way. Now, I can say a little bit more about what this quantization condition means, but let me say it in words because I'm completely out of time and I'm gonna stop and ask for questions. This, I can write it as integral of P of dx over a loop, right? Imagine the phase space. This basically, imagine a path in the phase space. Something like this. This, in a sense, measures the volume of inside the path. I know that I have not explained that. That's a little bit of differential geometry. This condition tells you that what has happened is that the phase space has become pixelated. Volume of this is not whatever number you want, because if it were whatever number you want, you could uncertainty relations do not allow you to. You would be able to like measure x and p simultaneously with an arbitrary precision. This is pixelated. The volume of this has to be a positive integer multiplied by fundamental constant. Now, fundamental constant tells you about how pixelated the phase space is. All right, so I'm going to pause here and ask for questions. I will have to next time, unfortunately, go over this half again and explain that. The symmetric argument hides the fact that this half appears, and I hadn't realized that. So we'll go through that again next time, and we're going to talk about the propagator. Any questions?
I guess what is the sort of quantization that your project being in? In my view, if you like solve the Maxwell equation, something finite units, finite stuff, or discrete stuff.
No, so the story of confinement, Maxwell equations, Maxwell equations doesn't confine, but that story is very different. That story is extremely different. So let's not talk about that. What I can say is there is an analogy between what you are trying to talk to, you're mentioning, and this. And the analogy goes through the following. There's a discussion in the context of differential equation called solitons. So solitons are exact solutions to differential equations that could be interpreted sometimes using methods like this. And solitons play an important role in this whole WKB approximation. So if you want to learn a little bit more about that, I can point you in that direction, but there's nothing sharp I can say in a couple of minutes. Yeah, that's a very more detailed study, thing. This I thing is profound. There is no, like, if you could understand this in very, very simple terms, understanding quantum mechanics would change. It's profound. Well, some might say that this is all that there is. This is the way the quantum mechanics works. But good. Any other questions? Remember that in the analogy between quantum mechanics and classical mechanics I was doing earlier at the beginning of part 2, I was saying that the density matrix, right, is like a probability, is a quantum version of probability distribution, right? Probability distributions are positive things, but this density matrix has had a bunch of phases, right? The distinction is something along these lines. E to the power of minus something is a positive number, a real number here, right? As opposed to e to the power of I something, the phase. Right? Yeah. Can you say it louder? Am I going to pose solutions? If you want a particular example, question, ask me. Yeah, particular one, and I'll post solution. Yes. Right, so let's just make a pause. Are there any physics questions before we switch to, because I'm gonna stop the recording. Any physics questions? All right, if not, please go ahead.